Greetings, aspiring scientists. Welcome to my video today on activation energy and catalysts for IB chemistry. So this will be the last video on rates of reaction for SL. Let's get into it and go to my slides. So here we are, reactivity 2.2.4, activation energy. I've already talked about activation energy in my previous videos. We should know that it's sort of the energy that has to be overcome before reactants can get to products in either an exothermic or endothermic reaction. So a little diagram here to show that again with an analogy of somebody trying to get a boulder from this high ground down to the low ground. It should be easy, right? Because lower ground is lower on the Earth's surface, but there's no direct path there. There's this hill in front that must be overcome. This is what we call the activation energy part of the reaction profile. So reactants will get to products only if they can get over the activation energy hump. And the only way to do that is to input some energy first. Somebody has to push this boulder up. So almost all reactions have an amount of energy that must be overcome before the molecules can take the path to the stable product. Now the top point is defined in energy terms as the least stable configuration of atoms and electrons that the complex must transition through during the transformation. So that's the highest point on that hump there on the hill, the very top. Once you get over that highest point, the reaction can kind of fall down quickly to the stable product point. So this one's showing an exothermic example, but endothermic is also very possible. Just that the products would be higher than the reactants in the end on the potential energy axis. Okay. So again, definition of activation energy: the minimum combined kinetic energy for colliding particles that is required for a successful reaction collision is known as the activation energy. So it can either be in joules for like one collision or joules per mole for bulk samples. And it's the combined kinetic energy, okay? So if one is not moving at all or very slightly, the other one must be moving very quickly. It's like EK1 plus EK2 must overcome this EA, the activation energy. Okay, when the sum of the colliding particles' kinetic energy is less than the activation energy, EK is less than EA, then the collision will not end up in a reaction. It'll just be a rebound kind of collision. Things might change direction and exchange some kinetic energy, but no new chemical compounds will be formed. But when EK is greater than EA, kinetic energy combined is greater than the activation energy, then the collision may be successful if the orientation is correct. We talked about orientation in my previous video. Things must be facing and hit at the right angle, and then, only then, might we have a successful reaction collision. So again, a little bit simpler profile here with the transition state clearly shown at the top of the hump. So the transition state is an unstable but real combination of atoms that must exist for at least a short time. The combination of atoms must pass through that point. It represents the position at the top of the activation energy. So you'll often be asked to draw this. So you draw a little point at the top of the hump where the transition state is, label it, and then draw a line straight up from somewhere where the reactants were, that energy. Draw like a dotted line there, and then a line up from there to the transition state. That's your activation energy sort of length and magnitude. Not to be confused with delta H, the enthalpy of reaction, which is the difference between the reactants and products in the end. So here's maybe a real example. This is a reaction that you'll learn later on in organic mechanisms. But consider this reaction bromoethane with hydroxide, OH minus, that will come in and kick out, substitute a Br minus to make ethanol, CH3CH2OH. Now this reaction has an activation energy, and it goes up to a transition state where one of these carbons here, the reacting carbon of the bromoethane, we'll have to form and break some bonds simultaneously at the same time. So we have the OH coming in on the left and the Br minus leaving on the right. And I think these numbers 2.43 and 2.24 represent lengths, maybe in angstroms or some kind of length units. So this carbon still cannot form more than 4 bonds, really, right? It's got a bond with carbon above it, it's got 2 bonds with hydrogen below it, and then the 4th bond is split between the Br bond breaking on the right and the OH bond forming on the left, so that's why they're drawn with dotted lines. But as you can imagine, this is highly unstable, and maybe a lot of the times it will not go all the way. The bromine will not fully break, the OH will try to come in and make a bond. It will be somewhat successful, but not overcome that hump on the reaction profile, and it will just fall back down to reactants. That would be a failed collision, either due to insufficient kinetic energy or bad orientation. You can imagine if the OH collides with like the CH3 group or too close to it, that's going to be a failed collision, or various other locations on this molecule. So this is the transition state for this reaction. Carbon has 3 full bonds and 2 partial, 0.5 or some percentage. We don't know if it could be 0.3 or and 0.7, but somehow one bond is broken up into 2 different parts. It still must have 4 total. So this transition state is highly unstable, but it must occur for the eventual formation of the alcohol to happen. So that's just one example, but this kind of thing happens for basically every chemical reaction. So practice 1, consider a single step reaction of the form A plus B goes to C plus D. Delta H equals minus 10 kilojoule per mole. So it's exothermic. The activation energy is 20 kilojoules per mole. Another important point is that activation energy will always be positive. It's always a positive amount of energy required. So A, sketch the energy profile. We can try to do that. We'll just start with the energy versus reaction progress sketch. So potential energy on the left, up and down axis. And we'll just say reaction progress. On the x-axis. So this is exothermic. We're going to have the regular profile for an exothermic reaction. Products lower. So we'll have C plus D down here, our products, and A plus B as the starting point. And we can draw a couple things on here. These are the energies of the products versus reactants. So we have delta H is minus 10. And we have an activation energy, which is from the reactants up to this highest point. EA, and that is equal to 20. Okay, now I think that's good enough. Deduce the activation energy for the reverse reaction. So maybe you don't even need to draw this, but the reverse reaction is just this kind of mirror image flipped, where C plus D goes to A plus B. So we'll start low, go up some activation energy, and finish high. But many of these distances or gaps will be the same, right? We're still going to have a delta H of 10, but this time it's plus 10 for endothermic. But our activation energy, you have to know exactly what it represents on this graph. this space from A plus B here up to the transition state is still 20. So the activation energy for an endothermic reaction going like this is from the starting materials up to the highest point of the transition state. So that would be a large arrow composed of 10 plus 20. Okay, so EA reverse is equal to 10 kilojoule per mole plus 20 kilojoule per mole. So that is 30. And again, it cannot be negative. Okay. Sorry, it got a bit messy there. Next. So we have to learn about something important called the Maxwell-Boltzmann energy distribution. Very important for physics and chemistry as well. And it's quite a difficult graph to understand, but we'll try to explain this. So the first thing we'll look at here is what's on the axis. There's relative frequency. So this is related to something called frequency distributions, or even histograms if you've studied statistics. So we have percentage on the y-axis, and then some property, which in this case is speed on the x-axis in meters per second. So basically what you would do is, if you want to know how many percent of your sample is at a certain speed, say 400, you can look up where one of these graphs intercepts 400. So if we look at 273 Kelvin first, the blue one, 400 would intercept right about there. That's right about 11%. Right? So that's the way that you read this graph. Check a speed and then find out what percentage of your sample is at that speed. And it should be true that if you would add up all of the speeds and the percentage representing each one, you should end up with 100%. Okay, it's hard to judge exactly how many individual speeds were put together on this graph, but you can imagine taking smaller and smaller differences in speeds, like 100, 200, 300, or 101, 102, 103, or 100.1, 100.2. Really depends on whoever made this and measured it, just how precise they were getting. But just looking at this, we'll make some assumptions. All right, so the total amount of percent should add up to 100%, cover 100% of your sample. And what else? So in this particular one I've shown on this slide, we've got 3 different temperatures. What can we notice as the temperature changes? So this is pretty typical of all samples of particles, atoms or molecules, but the lower temperature is shifted more to the left. It has a higher peak representing, a lot of percent at one particular speed. And it's got sort of a tall peak and then a quick fall to a thin kind of tail on the right. But as we increase temperature, 373 Kelvin, what happens? That peak on this kind of graph falls down a bit. The overall shape gets broader, and the tail doesn't fall quite as quickly down towards 0. But what we have to know, it's very important, is that, again, if you add up all the percentages in the pink graph, you should get 100%, same as for the blue graph. And we're assuming that this sample does not gain or lose any particles. So the area under both of these graphs, blue and pink, should also be the same. That's a key point. Pink appears to be more broad and more shifted to the right, but its peak is lower now. So that kind of area makes up for the new area gained on the right side. And then finally, if we raise temperature again for 73K, what happens again? That peak falls a little bit more. The graph shifts right a little bit more, gets a little bit more broad and less thin. And again, the percent should add up to 100. And the area under this should be equal to the area under the pink, which is equal to the area under the blue. All right. Important point on the right, sometimes these axes will have slightly different labels. You might have number of molecules on the y-axis, but that is essentially the same thing as relative frequency. Instead of percentages, though, you just have the actual number of molecules. So in that case, the area under each curve represents the total number of molecules in your sample, and it should stay constant. And on your x-axis, speed will sometimes be shown as kinetic energy. They have a proportionality relationship. EK is proportional to v squared, speed squared. So you'll sometimes see a graph with the kinetic energy values on the x-axis instead, but you read it basically just the same way. Okay, so a lot of my students have trouble understanding this, but what I often do to show them kind of what this is, a frequency distribution, is I have them go around and survey people in the class and ask, like, how many brothers or sisters or siblings do you have? And we often get a curve, something like 0, 1, 2, 3, 4, 5. So quite a few have 0. Maybe even more have 1. Less have 2. Less have 4. Almost none have 5. So we get this kind of shape. And I'll call this relative frequency. But you could imagine kind of like a bar graph for each of these values, right? Oops, I missed 3, but there should be a point there. We get something like this, right? And then you can imagine connecting the center of all of these bar graph bars and the point there with a kind of curved line. And this is kind of what the Maxwell-Boltzmann distribution is. It's just a frequency distribution of what happens when you try to count or measure how many particles have certain energies. It's just done with a lot more values, more particles, more different speeds, variabilities. So that's why I think it confuses a lot of students. Okay, so let's look at this in a bit more detail. Here are two temperatures, Maxwell-Boltzmann distributions of the same sample. So the area under T1 curve and T2 curve should be the same. But now I'm also going to show activation energy. Activation energy is just a point on the x-axis, a value here. You can imagine it like a vertical line, right? This line. Anything above that and underneath the area of our curve will be able to chemically react. It has enough kinetic energy, and if it collides and has the right orientation, we will have a chemical reaction. So for T1, what we have is the area that is above the activation energy on the x-axis and below our T1 curve. So it's this shaded area that's able to react if the correct orientation is met. What if we raise the temperature to T2? In that case, our whole distribution shifts. The way that I often like to imagine this is The temperature curve is kind of like a copper wire or a pipe cleaner, some kind of wiry shape like that. And when we raise the temperature, you're grabbing the end on the right and you're pulling it further to the right. I believe this graph would kind of behave in the same way as that wire. It flattens out, the peak gets lower, and overall the area underneath gets broader. So imagine we're grabbing that T1 curve on the right edge and just pulling it directly to the right side. We should end up with that T2 curve kind of thing, right? In that case, activation energy is not changed at all. That is key. Activation energy is that vertical line. It is not changed by changing the temperature. But the area underneath T2 curve now is much greater. So our new additional reactive particles are, I'll try to do in maybe purple. This is the new area. So the total amount would be that purple plus the red shaded areas. Okay, you got to really think and read what a question is asking you. Sometimes it asks what's the additional fraction of particles, that purple area. Sometimes it's asking what's the total. It is then the original red shaded area plus the purple. So that would be something like that total area, right? Add them together. Whereas the purple on the left here is just the new reactive particles. All right, so at lower temperature T1, very few particles have enough energy to react. As temperature increases to T2, the peak shifts right. A broader area under the curve means many more particles have the required activation energy and can react. The reaction rate increases with increased temperature. The rate will really depend on what the area is that's under the curve and to the right of that activation energy vertical line. All right, so practice 2. Consider the Maxwell-Boltzmann distributions from the previous slide. It's exactly the same. Now, if the same mixture was lowered to T3, cooler temperature, so T1 and T2 are greater than T3. Draw the distribution for T3 on the graph. Indicate the proportion of reactive particles which have the required activation energy at T3. Okay, this is a bit hard to do when the picture is so small, but I'll try my best. We'll do this in black, maybe. So, what do we know? When temperature goes up, the peak goes down. So if temperature goes down, the peak goes up. And we need a lower fraction of reactive particles underneath the curve and to the right of the activation energy. This should start at 0, 0 again, but go up sharply. Okay, we'll come up very sharply, start at 0, 0, and then come down sharply as well. Make sure we get a lower fraction underneath the curve that is to the right side of the activation energy. So this is T3, and our fraction that is reactive is the smallest of these three. It's this shaded area under our curve. And really this should just trail off to 0 here, right? All right, so something like that. Sorry, it's hard to draw on my screen here, but I hope you get the idea. Lower fraction for lower temperature. All right, so that's 2.2.4 done. We'll check out 2.2.5 next, catalysts. Finally, I've been talking about this for a while, but we'll officially define it. So definition of a catalyst: an element or compound which, number 1, provides an alternate transition state to lower the activation energy of a reaction. Second, is consumed in one elementary step and then regenerated in another. Overall, the catalyst is not consumed as the reaction proceeds. Okay, so the idea of an elementary step is an HL chemistry topic, but you can imagine just that there are smaller steps than what might be shown in a balanced chemical reaction. And so among these smaller steps, one of these steps will consume the catalyst, use it up, and then a future one will regenerate it, produce it as a product. So overall, our catalyst amount and concentration will not change, ideally. So this is part of the definition. Catalyst cannot be consumed. It's just present. It participates in the mechanism, how the reaction actually proceeds, but overall, not a changing amount or concentration. There's also some considerations for phases. So a homogeneous catalyst, just like a homogeneous mixture, this will have the same phase as the reactants. You could imagine a liquid chemical in a liquid solution. Compare that with heterogeneous catalysts, though. This is a different phase as the reactants. So if you put a solid piece of metal into a liquid or a gas inside a container, that's heterogeneous. We're going to have a phase boundary between solid and liquid or gas to have our reaction happen. But I think there are pros and cons, advantages and disadvantages to each. Some important considerations. If the activation energy is lowered, we just said a catalyst lowers the activation energy, then more particles on average will have the required kinetic energy for a reaction. Rate is therefore increased with the addition of a catalyst. And a catalyst not only provides an alternate transition state, but most often it will allow for the formation of a true intermediate and multiple transition states. Intermediates are much more stable and live longer than transition states, and in this way, a reaction with the catalyst can often be seen as a series of small exo or endothermic reactions sort of smashed together. And as I said, almost anything can be a catalyst, any kind of atom or structure or molecule. So intermediate and transition state. These are going to be two vocabulary words that you need to start getting used to, and it's easier to show what they are on a profile, I think. So here's a profile for some random reaction. We don't know what it is, but it looks like it's exothermic. We have delta H going down between reactants and products. And then we have an uncatalyzed transition state. That would be the profile on the top, just going up and then down, exothermic. Then we have a catalyzed reaction underneath it. So that catalyzed reaction has a smaller activation energy, EA2, compared with EA1 for the uncatalyzed version. Okay, and there will be this point in the middle here that is the intermediate. So why is the intermediate more stable than the transition states? It's all about the energy, right? This is our energy axis, potential energy. The transition states are very high energy, but the intermediate is less so. The intermediate's kind of in between the reactants and the transition states in terms of where it exists on that energy scale. It's like right here compared to our reactants that are there, compared to the transition states which are there or there. So if you're lower potential energy, you are more stable. Turns out that many intermediates are stable enough to exist for significant amounts of time. Okay, so my points on the right side here, the EA and the energy of any transition states are lowered with the addition of a catalyst. So overall, EA1 with uncatalyzed is quite large. EA2 is just that first hump there in the catalyzed reaction. It's much lower than EA1. And then an intermediate is formed which has enough stability to last for significant lengths of time. Sometimes we can even capture those intermediates with advanced laboratory techniques. And if you manage to do that, that's really good proof that you understand the mechanism by which this catalyst is acting. So that intermediate has a transition state on both sides, TS1 and TS2, those humps on each side. All right. Now, the enthalpy of reaction is completely unaffected. It is still the difference between the starting material, starting point, and the reactant, or in the products on the far right at the bottom. Okay, so here's the Maxwell-Boltzmann distribution for some reaction. And if we just look at the uncatalyzed version first. You can see the red or pink kind of area represents our reactive particles. So it looks like EA without a catalyst is 6.5 on some arbitrary scale here. So anything under our curve that is less than 6.5 kinetic energy units, not reactive. Anything above it can react though. But what happens when we add a catalyst? In this case, what we do is shift that activation energy vertical line back. Shift it to the left. New one here. With catalyst, it is 3.8, it says. Now our new reacting particles are in this kind of blue-green section. This new area is now available for reaction. And then the total is that new area plus the old one. So all of that shaded area can react. Those particles will have enough kinetic energy on collision to have a reaction with the right orientation. Okay, I also want to show a little video from a simulation I made with Claude AI, messing with the temperature and the activation energy amount. So first, if we change the temperature, we can see the fraction of reactive particles increase as we raise the temperature. The graph shifts kind of to the right. If we lower the temperature, it shifts back. Fraction goes down. If we add catalyst, boom, we just shift that activation energy vertical line to the left, and we get a whole new area that is now available to react. So hopefully you can see that. There's some percentages also shown there. So let's consider a real example. IB used to love this example in various textbooks, but I don't see it so much anymore. But I still think that there's a very good chance this reaction will show up on exams again in the future. So it's the reaction of ozone. So there's natural reactions of ozone. O3 goes to O2 plus O dot. O dot is an oxygen radical, meaning it has unpaired electrons. So you might remember the O3 Lewis structure is something like this. 3 oxygens, 1 double bond, 1 negative charge, and 1 positive charge. So we're going to come in, I think, basically cut this bond and get an oxygen radical and an O2 molecule. And this is done, I think, with the absorption of UV light. Mainly drives this. So that's how we get over the activation energy. Once that happens, O dot is very reactive, so it will react with whatever is nearby. If it reacts with O2 again, it'll just reform O3. And that way, this is exothermic. And the top one is endothermic. So basically, we're transferring UV light energy. It's absorbed as the activation energy of the top reaction, and then the exothermic reaction releases heat underneath. So basically, there's a transfer of UV light energy to heat energy, just as O3 is broken apart and reformed. But there's another possibility, which is O dot, the radical with unpaired electrons, reacts with an O3 molecule. In that case, that's broken again, and we end up with 2 O2 molecules. So overall, if that were to continue, the O3 in the atmosphere would break down into O2. Luckily, this is kind of slow, and we don't really want the ozone to break down in the atmosphere. It serves several functions, like transferring UV light into heat, instead of having it reach the surface and giving us sunburns or destroying plants or causing other various unwanted reactions. So O3 is naturally broken down by UV light from the sun, but can reform in an exothermic reaction. Overall, UV light is converted to heat. Alternatively, it degrades slowly to O2. But then we have a problem if there are such things as chlorine radicals also in the atmosphere. Normally there is not, but due to human activity, we have released quite a lot of what are called chlorofluorocarbons, organic molecules that have carbon, fluorine, and chlorine. So here's a difluorodichloromethane, CF2Cl2. If this is in the atmosphere, it can also react with UV light, and it will release a chlorine radical, Cl dot. So that's a chlorine with an unpaired electron. Again, looks something like just the elemental Lewis structure for chlorine with an unpaired electron. 7 electrons on that chlorine. All right, and now once that forms, that can participate in the ozone reactions as well. Cl dot plus O3 goes to ClO dot plus O2. And then further on that, ClO dot plus O3 goes to Cl dot plus 2O2. And this goes much faster. The activation energy required is much less, and the transition state, the intermediates, are more stable. And the overall catalyzed reaction, if we just add these together, will cancel out ClO dot and Cl dot, one on each side. So what we have is just 2O3 goes to 3O2. So overall, ozone being just broken down into oxygen, and it goes fast. And the problem is this reaction requires Cl dot, but Cl dot is produced as a final product, right? Which is why it doesn't appear in the overall catalyzed reaction. It's just that this is catalyzed by Cl dot. The Cl dot never actually goes away. It's regenerated, so it can just do the same reaction again. All right. So we can try to show these on some reaction profiles. On the top, we'll just have the reaction between ozone and some oxygen radical. That is a sort of one-step, single transition state conversion across the top. 1.5 O3 plus 1.5 O dot goes to 3O2. Okay, I had to add the 1.5s in order to compare this with the chlorine reaction. So overall, we should have I think 6 oxygens in this reaction, right? 1.5 O3 is 4.5 O, and then plus 1.5 is 6, yeah. So I'm just trying to compare the production of 3 molecules of O2 between these two methods. That's why I'm using these stoichiometric coefficients. But what happens if we mix O3 with Cl dot instead? We get our intermediate position, which is ClO dot plus O2 plus O3, and then that ClO dot will react with the O3 on the right side and break it apart. So in the end, we end up with 3O2, and Cl dot is regenerated. So you can see the activation energy for the uncatalyzed reaction is much higher. That's going to slow down the rate for sure. The activation energy for the catalyzed reaction in orange, much less. We have a stable intermediate, that's the ClO dot. It's still not very stable, but compared to the transition state for the uncatalyzed reaction, it's quite a bit more stable. And then it will fall down to the products. So note the differences between the oxygen radical and the chlorine radical. In the uncatalyzed version, O dot is consumed. It doesn't show up again. And there's a single transition state, higher activation energy for the uncatalyzed reaction. Okay, kind of a random point here, but I think is important because sometimes shows up on exams. But recently, our vehicles often have catalytic converters in the engine. That's to try to reduce harmful emissions, for example, nitrogen oxides or carbon monoxide. So we can have things like NO goes to N2 and O2, fairly inert, non-problematic gases compared to NO. Same thing for NO2, we can form N2, N2O2, much more favorable emissions. And then CO, which is highly toxic, plus O2 goes to CO2. It's kind of just like double combusting that, or making sure it goes to complete combustion. We can do that with a good catalyst. What is the catalyst? It is usually some metal, maybe platinum, palladium, rhodium, vanadium, copper, chromium, some of the transition metals. Why are they good catalysts? We're not really going to go into detail here, but it has to do with the fact that they can form many bonds and they can have many oxidation states, 0, 1, 2, 3, 4, 5, 6, depending on the metal. And metallic oxides are sometimes used as well, copper oxide, iron oxide, various things. But I think all you need to know is basically what's on this slide. Don't memorize all the metals, just know that it's often a transition metal. And then practice 3, consider the following reaction. 2SO2 plus O2 goes to 2SO3, delta H less than 0, that's exothermic. Now when NO2 gas is added, the rate of this reaction increases by 4 orders of magnitude. That's like 10,000 times faster. It follows a new set of steps. SO2 plus NO2 goes to SO3 plus NO, step 1. And then NO plus 0.5 O2 goes to NO2, step 2. State the role of each nitrogen oxide in this process. So we have 2 nitrogen oxides, right? NO2 and NO. What is NO2? You've got to look at how it reacts and how it finishes. So it is consumed in step 1. As a reactant, but it is produced in step 2 as a product. So overall, it will not appear in an overall chemical reaction. And we also know when it's added, the rate increases by 4 orders of magnitude. So this is the definition of a catalyst. Used and regenerated, speeds up reaction rate. What about NO? NO, look at it. It is produced in step 1. And then it is consumed in step 2. So it will appear, but then immediately disappear. It also will not show up in overall chemical reactions, overall balanced chemical equations. So that is the definition of an intermediate. All right, NO2 is a catalyst, NO2 is an intermediate. Very good to be able to find these from these sort of elementary steps. Things that are consumed and then produced are catalysts. Things that are produced but then consumed immediately are intermediates. Okay, number 2, sketch a reaction profile for the uncatalyzed and catalyzed reaction. Label all species, intermediates, and transition states. Okay, let me clean this up a bit. I'll draw it here. Okay, I'll try to make this big. Here's our profile, energy here. Progress. So this is exothermic. The original reaction is a single step uncatalyzed. So maybe it starts here, goes up to one transition state, goes down to products. So we just have SO3 as the product, and the reactants were SO2 and oxygen. I'm going to use just 1 mole of SO2 so that I can compare with the catalyzed version. So SO2 plus 1/2, 0.5 O2. Okay, so SO2 plus 0.5 O2 goes to SO3. That's our uncatalyzed. We will have a transition state here. All right, next the catalyzed version. So this will start basically in the same spot, but this will be SO2 plus NO2. And later on, we do have to use some O2, so I will also include that, 0.5 O2. This energy represents the energy that all these three things are at. So this will go up to one transition state, down to an intermediate, up to another transition state, and then down all the way to the products. Okay, so we've got intermediate there, transition state there, and transition state there. We can call these transition state 2 and 3, maybe. And what is our intermediate? It's that equation on the right of the first step, SO3 plus NO, and our 0.5 oxygen that's required for the second step. Okay, and when it goes down to products, we have SO3, and then our catalyst, NO2, is regenerated. Okay, so catalyst is used to make the intermediate, but then is regenerated as the intermediate reacts. Okay, you could also label all of delta H and the activation energies in this. The activation energy, there's not really enough space to show it, but I just want to show for the uncatalyzed reaction, it would go down to here. And for the catalyzed reaction, it's to the highest point on that whole profile, which is transition state 2. Sometimes it will be transition state 3 that could be even higher. That will be the activation energy from the baseline up to that. But here, TS2 is still higher, so this is EA2, we can say. And that was EA1. Okay, getting too crowded there. That's enough. So what about catalysts in biology? Living organisms have evolved highly specialized catalysts over millions of years. These catalysts are proteins, also known as polyamides. They have amide linkages, kind of like biopolymers. And then these fold in specific ways to force certain transition states and intermediates in reaction pathways. So they can accelerate reactions which would take millions of years down to a few milliseconds in the bodies of cells or bacteria or plants or animals or whatever. Now, you might not be interested in biology if you're studying chemistry, but even so, you should always consider that there may be a biocatalyst, some kind of enzyme, protein, polyamide, that can accelerate your reaction and save you a ton of energy on heat or concentration or grinding things. You know, it might be possible to do your reaction much more simply with a biocatalyst. So here's a diagram that I got from mun.ca. It's, I think, a university in Eastern Canada, but shows well here what will happen. Your enzyme catalyst has two active sites, these two kind of red stars. Substrates are what are known as the reactants in biology. So the substrate reactants come in and they're attracted to these positions, the active sites. They will fall into place, and then the enzyme complex will fold and sort of compress these things in such a way where they are held together for significant amounts of time, and the correct orientations are basically set by this enzyme. Once the reaction happens and the product is complete, the enzyme then releases the product. So this can make things go much faster than if we're just trying to wait for random collisions to get the right speeds and orientations and configurations. So biology is quite amazing for producing these enzyme proteins. All right, and the last practice for today is just to fill out this table. So we have various different factors, changing concentrations, pressures, volumes, catalysts, whatever. And then we want to consider how this affects different things with regards to a reaction. The frequency of collisions, the average EK of reacting species, the activation energy, and then the rate of the forward reaction, just the rate of the standard reaction. So you can try this if you want, but I will go through it now. So, frequency of collisions. If we decrease reactant concentration, what will happen to this? Decrease. We saw in my previous video that lower concentration means lower frequency of collisions. What will happen to the average EK, kinetic energy of reacting species? No change. Simply adding more things or decreasing the volume, that's the way we can change the concentration, right? C equals N over V. But these things, number of particles and volume, will not affect the kinetic energy whatsoever. All right. Activation energy. Decrease reactant concentration, no change on activation energy. The required combined kinetic energy is still the same. Rate of forward reaction. Well, if we have lower amount of collisions and no changes anywhere else, rate depends on collisions, so decrease rate. Okay, next row. Increase in pressure of a gaseous reactant. Frequency of collisions increases, we saw that. So we had PV equals nRT. In other words, P equals nRT over V. So you can either add more particles, increase the temperature, or decrease the container volume to increase the pressure. But whatever you do there, the frequency of collisions will increase. Average EK though, no change there. It's really only the temperature that can affect the average EK. So unless you raise the temperature, unless you raise the pressure by raising the temperature, which I think we're assuming is not the case here, then there's no change. Activation energy, no change there as well. Then the rate of forward reaction, this will increase. The only change we had is increased collision frequency. That's good for rate. Decrease in pressure of a gaseous reactant. This will decrease frequency of collisions. No change on the EK. No change on the activation energy. Rate of forward reaction then will decrease, fewer collisions. Okay, next row, increase in volume of a gaseous reaction mixture. Frequency of collisions will decrease there. We saw that. This will be essentially lowering the concentration. Average EK, no change. Activation energy, no change. Rate of forward reaction, decrease. Fewer collisions. Decrease in temperature. Okay, finally we get into temperature. Decrease temperature, we decrease the frequency of collisions. Less chance that they will hit each other, or particles. Average EK of reacting species, we also decrease this. activation energy, this still does not have any effect on the set activation energy of some reaction, some transition state. But the rate of forward reaction definitely decreases. We have two factors that decrease it here. Next, increase in surface area of a solid reactant. Frequency of collisions, increase. Higher surface area, more spaces for particles to collide and have collisions. Average EK, no change. It's really only the temperature again that can change the average EK. Activation energy, no change. It's still a set amount. Rate of forward reaction, increase. We have more collisions available on that surface area. Okay, finally, addition of a catalyst. Frequency of collisions, no change. Catalyst doesn't affect that. Average EK of reacting species, no change. Again, only temperature can do this. Activation energy, though, this is the one case where your activation energy will change and decrease. We just saw that's what a catalyst does. Its main function, provide an alternate pathway, alternate intermediates and transition states. So the set number of activation energy can decrease in this one specific change of parameters. And if the activation energy decreases, it has an inverse relationship with the rate, so the rate will increase. Done. All right. I'd really recommend you know this. It's kind of memorization, but it will make sense if you really understand collision theory and the way that changing these parameters changes collisions. Also considering kinetic energy of collisions, orientation, and frequency, right? Okay, that's all for today. Hope you enjoyed and learned something. I think I'll probably make a paper 1A multiple choice guide video for the upcoming November exams. And then we'll move on to equilibrium next. All right, have a good one. See you later.